All right, so we will start the lesson now. Now, today we would focus on some other experimental method of determining the enthalpy terms. So today we will introduce something about the reaction involving the solution. Okay, so you are going to or between a solid and a solution. Now, this is different from your original design, right? The old design last week. So this one is just for burning. Okay, it's for determination of delta H of combustion. Can you see that? So, and we would focus on some other reactions in which it will mainly focusing on the mixing of two solutions or the solid and solution. Okay, so this is another type of calorimeter. So you will see that is a type of another type of calorimeter. So we will have a some setup. Okay, like this. Now I would like to show you the video, or please take a look on that and then tell me what is the advantages of such a setup, okay? And how do we measure the delta T of the solution in which it will help you do the calculations of the standard enthalpy change of a reaction that later on. Okay, so two questions. One is, why is there such a design? Any good points of making such setup? And number two is on the mathematical calculations. How would you get the data and how would you make use of data to get the enthalpy terms that we want? Okay, is that clear? So I would like to show you this one. Can you hear some sound?
Hello.
Yep, thank you.
In this experiment, we are going to measure the enthalpy change accompanying the neutralization reaction between hydrochloric acid and sodium hydroxide solution. We will use 2 moles per cubic decimeter hydrochloric acid and 2 moles per cubic decimeter sodium hydroxide solution. This is an expanded polystyrene box filled with cotton wool. This is a plastic cup. They form a calorimeter. This is a stirrer, and this is a thermometer. First, place 25 cubic centimeters of hydrochloric acid into the calorimeter. Then measure the initial temperature of the acid and record the data. This is 25 cubic centimeters of sodium hydroxide solution. Measure its initial temperature. Next, pour the 25 cubic centimeters of sodium hydroxide solution into the calorimeter and take the maximum temperature of the reaction mixture. We can use the data to calculate the enthalpy change of neutralization. The average initial temperature of the acid and alkali is 27.8 degrees Celsius, and the temperature rise of the reaction mixture is 12.2 degrees Celsius. Assume that the density and specific heat capacity of the reaction mixture are the same as water. We can calculate the heat released by the reaction as follows. The number of moles of water formed is 0.05 moles. Hence, the enthalpy change of neutralization is equal to 51.0 kilojoules per mole.
So, all right, so you may see the calculations as well as its experimental design. Now, take a look on the design and check it against the one with the video. Any difference?
Stirrer.
Yes, stirrer. Yes, there is a stirrer, right? There is a stirrer, right? What else? So stirrer, so it's made up of usually is made up of copper wire stirrer or any metal stirrer. So so how you stir that? You have got to bend as a shape like a ribbon in the at one end and use this for help to stir. Okay, so this is the first one. And what else? What else is different? Cotton wool. Where you will find cotton wool? Where you find cotton wool? And then you just mentioned cotton wool. Where we will place the cotton wool? Now, do you see the beaker? Do you see the beaker? Between the spaces between the polystyrene cup and the beaker, do you see the beaker in the video? What you'll find in the exterior? What you'll find? Is it a beaker?
個 video 係用咁用expanded polystyrene 咯。
Yes, another foam plastic box, but not a beaker, right? So it will be something like this. I would expect, I would think the design would be something like this: polystyrene box. So whether or not there is a beaker, I don't know, but you may see some trace of cotton wool here. Right, this is another type of design. So it seems like a black box. I don't know whether or not there is a beaker, but I would also expect that the container may not be a beaker. Instead, it is polystyrene cup. Of course, we've got a polystyrene cup as well as the lid, right? It is also made up of polystyrene. It will be something like this. So I don't know. I don't know whether or not there is a beaker, right? But I would take a look at the certain angle, right? There may be some cotton wool, which is used to wrap the container inside. I do suspect that will be so, and together with it, right? So all those, what are the purpose of all those? What are the purposes of all those? Now, whatever what design we are having, what are the purpose? Are you here?
Yes.
Tell me the purpose of such design, the one we show the video or the one shown in the book, all right? We'll use mainly cotton wool and or polystyrene cup or polystyrene material, that material.
To prevent heat loss.
Yes, the heat loss. Heat loss to where?
To the surrounding air and the cup.
Okay, to the surroundings. While in physics we talk about surroundings is on here. Now, so this is our system today. Okay, this is a system. While the other places other than the system we call the surroundings. So it can be the container, the thermometer, the stirrer, the air, right, etc. So it depends on whether or not there is heat transfer between the solution and the other material. In physics, you may heard of there are 3 modes of transfer, right? Conduction, convection, radiation, right? So all those, they are so in chemistry, we need not take too much care about what specific type of heat transfer it will be, but in generally speaking, all those design helps to prevent the heat loss to the surroundings. For example, so you may see that why, first of all, why would you choose polystyrene cup? Because it is a very excellent heat conductor. Okay, so and it has a negligible specific heat capacity, so it will not increase the temperature, or it is a very poor heat conductor. So which means that less heat will be transferred to the surroundings of the cup. Of course, the lid, what would help, right? Just like what you are having in winter time, right? We have got a hot cup of tea. You better have a lid so as to prevent heat loss, right? While you know the mode of heat loss is by convection. You know it? Convection 對流. So the airflow, in a certain direction. And no need to mention the material of the cup. The material of the cup is made up of polystyrene when compared with, for example, metal. Okay, for example, ceramic is different. So this one, they will help hold more heat in layman terms. But in science terms, it's a very good heat insulator. Okay, a very good heat insulator, which will reduce the heat loss to the surroundings. So no need, it's not just polystyrene cup, but indeed, how about cotton wool? Cotton wool, it is also a heat insulator, but inside that, we have got 2 materials. One is cotton, the other one is air. Air is also a very good heat insulator if I resist its flow. Okay, can you get my point? Where I resist its flow. So that's why if you have got if you allow them to have a flow of air, we would produce convection so more easily. So it is also a mode of heat transfer. You know what? For those who study physics, you should understand what I mean, right? So for those who did not study physics, don't worry, it's something about common sense. Okay, so what design that you have, the ultimate goal is very simple, is to reduce the heat loss to the surroundings. So can you get my point? So this is how we can calculate the delta H of neutralization. Now remember, while you do the experiment, remember to measure the temperature of both acid and alkaline. Okay, because that 2 chemicals may not in the same temperature. Of course, we may argue we just take it in from a room temperature. How come is in different temperature? It's uncertain, right? It's uncertain. It depends on the chemical inside. Okay, it also depends on the brand of a thermometer. Okay, so it may cause you certain type of discrepancies. But anyway, what you need to do is our common practice is to measure the temperature of the 2 solutions first of all, and then try to make an average initial temperature of the solution. So it is just 26.6 plus 26.x over 2. So this is the initial temperature of the solution. While you know that you get mix of the 2, the exothermic reaction of neutralization being exothermic will release heat instantly. So you use the temperature thermometer to measure the maximum temperature. So by counting the difference. So this one, it is T initial, while this one is T final. Delta T is just T final time minus T initial, and so you may get the delta T. Can you get my point? So afterwards, so this is the one. So afterwards, what you need to do is to think of MC delta T, right? E is equal to MC delta T. So C, delta T, I know it. Just a temperature change, is a temperature rise. How about C? Is a specific heat capacity of the solution, while M is the mass of solution. So it depends on the design of experiment. If you have 25 ml of acid and 25 ml, 5.0 ml of alkali, usually they will use pipette, right? But not measuring cylinder if you want to make it more accurate. So by doing so, you may get the total volume of the solution being 50.0 cm3. And I assume the density of the solution mixture is also 1.00 gram per cm3, such that I can get the mass. Now, of course, it doesn't make sense, right? Because the solution is not pure water. Okay, it is with some other minerals. Okay, it is sodium chloride. So the density of the solution may be a little bit changed. No need to mention its specific heat capacity of the reaction mixture. I would use the data of water for calculations. So that's why during the whole calculations, you may soon realize that because these two data is just based on assumption, right? Having the solution, the mass of solution, the density of solution, and the specific heat capacity of solution being equal to that of water. Can you see that? Can you see that? So, what you finally calculate this one, it is the delta. Is just a heat released. It's a heat released. And remember, because of the enthalpy terms, you need to mark it per mole. You have to calculate how many moles of water can be formed from this reaction. Now, so nice that we have got monobasic strong acid and another alkaline to react. They are in equal moles. So it's 0.0250 mole. Water to be formed is also 0.0250 mole. And what you're going to do is to divide 1.38 kilojoule over 0.250 mole. Now, remember, you are going to make it heat produce. Of course, no sign here. Can you see that? Heat produce, no sign here. But once I change it to enthalpy change of neutralization, can you see that a very long term of hydrochloric acid and the sodium hydroxide solution? It is this. So with a minus sign here, which tells you it is an exothermic reaction. Heat is released. And with a unit, kilojoule per mole. Per mole here means per mole of water produced. Okay, is that clear? So remember, whenever you write down heat released, heat produced, per blah 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 chemical, and it carries no sign. But once I change it to the terms enthalpy change of reaction, for example, it must follow with a sign. Okay, net minus sign for exothermic, positive sign is for endothermic reaction. Any questions? You know how to calculate this? So in short, you need to have two data. One is E is equal to MC delta T. It is what you can calculate as a amount of heat transfer to the reaction mixture. And the calculate the amount of the water form, you need to check the equation. Okay, you need to check the number of moles of acid, alkali, and hence water will be formed. And I use the number of moles of water to be formed as the starting point, right, for you to do the calculations. So once we have got that two data, what should we do? Is to simply have this E and then number of moles of water, put a minus sign here. Is that clear? So this is what we do the calculations. Questions? Now, if not, let's have an error analysis, right? So the answer calculated above is different from the value quoted in the data book, suggests a possible sources of error. So data book, so you usually see another term, we call that literature value. Okay, the literature value, which means the value that you got it from their own design, right? From the most accurate design, so with least errors. So usually people, after doing your own experiment, they would try to use this data to check against, okay, the literature value and do some error analysis. So this is our common practice. Any suggestions of errors? One it long. Anything about the experimental design or the mathematical calculations which will cause certain errors? Now, it is calculated by 55.2 kilojoule per mole. So what is the literature value? First of all, before you do the calculations, do you know the literature value for this delta H of neutralization between HCl and NaOH?
57.1 kilojoule per mole.
Sign, what is the sign of the data?
Minus and negative.
57.3, is it, or 57.1?
0.1.
0.1, okay, unit is kilojoule per mole. So this is the literature value. While you calculate is minus 55.2 kilojoule per mole. So the experimental data is less exothermic. It's calculated to be less exothermic. So there should be some heat which we can't be measured, right? It seems that less heat is released. What are the possible sources for errors? You may type
heat loss to surroundings.
Yes, but it is unavoidable, isn't it? It's unavoidable. Heat loss to the surroundings is unavoidable. So other than the solution mixture, there are some heat loss to the surroundings. For example, in the solution, if the design of solution is like this, okay, of course, there are much heat loss to the surroundings. First of all, by convection of air, right? The airflow, they will do that direction. Do you still remember? According to physics, right? You have got some flow of air, so it will bring away your heat, right? So you heat loss will be through here. What else? About the design, cover polystyrene cup. Now they absorb heat, but not so great amount. Thermometer that is made of glass, it can also absorb heat. The stirrer also absorb heat. Do you realize? So you may mark it here. For example, air. So the polystyrene cup, the stirrer, the thermometer also absorbs heat. Okay, what else? Can you see the experimental condition? Do you know what is the experimental conditions they are doing 26 point something degrees, right? So how about the literature value? Do you know what are the conditions to be measured? Can you see this? With this sign, what does it mean by that?
Standard condition.
Standard condition, please define standard condition, DSE type question, right? Please define. Temperature, first of all.
25 degrees Celsius.
Yes, 290 Kelvin with 1 atm, while the solution being measured as 1 molar of solution, right? So all those, they are not in line with our experiments. So the experiment is not carried out under standard conditions. So based on the initial temperature of the solution, I will soon realize that it is not. So this is different. Okay, is that clear? So you may think of some other areas like this. Okay, so this is what you know about the area analysis. Any questions so far? Now, how about the other cases for determining the enthalpy change of the displacement reaction, for example? Now, it's a very authentic example which involves a reaction between the solid and solution. Do you realize? It's a measurement of the temperature of the solid and solution. And you are going to read that paragraph, okay, here, first of all. And what you need to do is to check, is to watch the video that follows and try to tell me what is the difference between the experimental design as well as the mathematical calculations that follows. Now, this is what I would like to ask you guys to be more aware of. Now, please take a look.
In this experiment, you are going to determine the enthalpy change of the reaction between zinc and copper 2 sulfate solution. Using a pipette and a pipette filler, transfer 25.0 cubic centimeters of the copper 2 sulfate solution into the calorimeter. Weigh out about 6 grams of zinc powder into a weighing bottle. Zinc is in excess. Place a thermometer through the hole of the lid of the calorimeter. Stir the solution and record the temperature every half minute for 2.5 minutes. At the 3rd minute, add all the zinc powder. Continue to stir and record the temperature every half minute for an additional 10 minutes. Join the points before the addition of zinc powder using a straight line and extrapolate to the 3rd minute. Label the temperature at the 3rd minute as Ti. Join the points after the addition of zinc powder using a straight line and extrapolate back to the 3rd minute. Label the temperature at the 3rd minute as Tf. The separation of the lines at the 3rd minute corresponds to the maximum temperature rise for the reaction.
So you may see this is the design, they are more or less similar, right? But tell me, but anyway, there is a slight difference between the two. Okay, tell me the difference. Any minor difference between the two in terms of the design? What else? Before we talk about mathematical calculations, first of all, design. What is the difference? Tell me the difference between the two. Cyrus.
In determining the enthalpy change of neutralization, an expanded polystyrene box is used.
And then?
And you
How about the use of chemical? They relative.
In determining the enthalpy change of neutralization, you have to use measure the volume of 2 solutions. While in determining the enthalpy change of a displacement reaction, you only have to determine find the volume of 1 solution and then weigh out. It could be in excess.
Solid should be in excess. Can we measure the temperature of a solid accurately? Do you realize, right? You didn't measure the temperature of solid instead. Now, so you according to the same logic, right? So originally for neutralization, all 2 reactants with the temperature to be measured initially. But for displacement reaction, we need to measure the temperature of solid. Why? Cyrus, do you realize? We need to measure the temperature of solid. Hi, are you here?
Yes.
Yeah. Do you realize?
We don't need to.
Yes, we do
measure.
need to.
We don't need to.
We don't need to, but why? Is it possible if we can measure the temperature of the solid in order to make the results more accurate? You find you just stress that is not necessary.
Is it use the powder and measure it at the thermometer?
Now it's rather impossible, right, to measure the temperature of the powder, because what type of measurement it is still not possible to calculate as accurate as possible, because it's not just powder that touch the bulb of a thermometer. It's also the air. Okay, it's also the air. So So practically, it is impossible to measure the temperature of the powder. And what's more is that what Cyrus has been mentioned is on the solid, the zinc powder should be in excess. Okay, while for the neutralization, we usually make the two chemicals just react. So this is something different. So what is the purpose of having zinc powder should be in excess? For insurance, right? For something. To ensure something. Once again. Once again.
係，但我聽唔到，唔係好清楚，可唔可以講多次個問題？
I just underline this. Tell me why.
等 ensure 嗰個complete reaction。
Complete reaction. Complete reaction. Theoretically, practically, you cannot, because zinc will remain undissolved when reacted. So the reaction is not complete. So it depends what is the role of the chemical you are talking about. Can you get my point? If you make one chemical is in excess, of course, not all chemicals will be completely reacted, including zinc, right? Zinc is not. Yes, that's right. You change a little bit of the term, but too general to say that you need to ensure the complete reaction. But the ore copper 2 sulfate, okay, will all be reacted. So this is the answer. Do you realize the difference between the two? And I soon realize that you better brush up your skills while you do the chem essay. Do you realize some others? Why we have got the same topic? Some of you can go say score 5 marks, but some of you can just score 1 or 2 marks. So the difference lies on the use, the proper use of the terms. Okay, you are going to use the precise and concise term. But while you talk about the chemistry, you realize, so you are going to ensure ore copper 2 sulfate has been reacted, but not saying that to ensure there is a complete reaction. Theoretically and practically, in this solution mixture, the reaction is not complete. Can you get my point? So what is the significance of having copper 2 sulfate all be reacted? What is the significance behind? So is it something related to the calculations? Okay, the calculations. Why do I say so? So do you find it? Now let's check on the calculations part. Now, first of all, the copper sulfate, what is the glassware to be used? Now, so you see that for the calculation amount of copper sulfate reacted, I use this, and they put it in the denominator. So you may find that this one should be all reacted. Only by making all reacted, if I express kilojoule per mole is for copper 2 sulfate. So they can reflect the enthalpy change of the reaction. Can you get my point? So that's why, in order to make that data valid, first of all, I need to put excess zinc powder to make sure that all copper 2 sulfate have been reacted. And from the glassware, what glassware do we use to make sure the chemical delivered is 0.0125 mole? What glassware do we have?
Pipette.
Yep, pipette. It is 50.0 this time, 50.0 cm cube pipette. I use this to ensure the chemical is just delivered as per what you calculate. Okay, it's 50.0 cm³ pipette. Is that clear? So the measurement of the temperature should be made every 30 seconds for 2.5 minutes. And it's for what? It's to measure the true initial temperature of the solution. Do you realize 2.5 minutes? So even though you have got the thermometer I place in air, the temperature is different from the one in the solution. There is some difference. Okay, so that's why. But just like while you are having fever, for example, these days, while you put the thermometer, while you do the clinical thermometer directly into your mouth, can you just directly put it out and measure the temperature, the room temperature? The answer is not. Usually, we try to put it in the mouth and stay for some time. This is still the same thing. Do you realize? So it's a very traditional way of measure the temperature using that type of fluid thermometer. But of course, nowadays you use very certain like IR thermometer, such like this, right? So it's another principle. And then at 3 minutes, add the zinc solution in the zinc solution and stir the mixture, and then measure the temperature of the solution mixture every 30 seconds for the further 6.0 minutes. Do you realize? So why will be the following step so clumsy? Now, indeed, this is necessary. What is the difference between displacement reaction and neutralization in terms of speed of reaction, in terms of rate of reaction? Which one is quicker? Which one is slower? Displacement is slower. Can you realize? While for neutralization is quicker. Why? It's just a direct collision of hydrogen ion and hydroxide ion in the aqueous medium. Now, if you talk about neutralization, while for displacement reaction, the reaction will happen in where? Where? On the surface. So the reaction that will happen on the surface, while of the zinc and the copper 2 ion, okay, on the surface. So the reaction is rather slow. Displacement reaction is rather slow. So you can never measure the true maximum temperature of a solution. Why? First of all, while you release heat, it will spend you some time from here to here, more than 1.5 minutes. Okay, the release of heat will happen in that 2.5 minutes. Do you realize? But at the same time, there is also one important heat transfer, which is what? Heat loss to the surroundings. While this continues until the solution mixture would have the same temperature as the room temperature. Do you realize? So we can never use, for example, the so-called local maximum, and you mark and do the initial temperature, and you can measure that is the delta T maximum. Now, so if you do so, it is wrong. Okay, it's wrong. It's because this one is not a maximum temperature. Why? Because it is even though the heat has stopped releasing heat, we have already gone through 1.5 minute heat loss to the surroundings. So that's why, even though I mark it as 35.0 degrees Celsius, it doesn't reflect the maximum temperature. So some heat has been lost. Do you understand? So what can we do is to project the true maximum temperature rise of the of this solution mixture. How? So keep track of this. Okay, after that local maximum, what will happen? It will show a gradual decrease. In the temperature of the solution mixture. Do you realize? So that type of decrease is rather steady. So what is that? So, well, it is also a type of reflection of heat loss to the surroundings. Do you realize? So you use this data, you use this trend to project to the point where the two chemicals just react. So this is 3 minutes. So the zinc, just add zinc to copper to sulfate solution. So you are going to imagine that is the timing where the zinc and copper to sulfate all react at that moment. So it happens at the 3rd minute. So you can do such projection at 3 minutes and you can get this. That's imaginary data. So it is the imaginary, the maximum temperature. So of course, if you write down imaginary, it is rather subjective, isn't it? Now, it is something about, but that type of so-called not true data, it is indeed based on some scientific findings. It is from the projection of the gradual decrease in the temperature of solution and you project it upward. So we will not say it like this way. We go this type of technique, extrapolation. Can you get my point? Extrapolation, 外推法. Okay, this is a technique where we can locate the maximum temperature so as to calculate the maximum temperature rise. So you may see it is it's now calculated as 36.0 minus 24.1. It is the initial temperature of solution. It is being 11.9 degrees Celsius. Remember the technique, extrapolation. It is done by having two lines. One is this one. You draw this. Of course, you have make use of the 2.5 minutes to make a steady temperature. So of course, it is a horizontal line, and that another line comes from here. First of all, find the gradual decrease in the temperature of solution mixture, and you use this. What is meant by extrapolation? You're going to extrapolate that line up to where it is 3 minutes. So it is the 3 minutes. The 3rd minute is the place where the two chemicals just react. So what's next? The 3rd point is to draw a vertical line. So we have got 3 lines, right? With two intercepting points. It is intercepts. So you are going to find that 2 points, to find the difference. It is the delta T. Is that clear? You understand? So you usually use that type of method in so many calculations, in case of thermometric titration, etc. Right? You may see that data again and again. And use this 11.9 degrees. So you are going to use MC delta T. So what is M? What is C? What is F delta T? It's very strange. Can you see that? 52.0 gram. Why is it 52.0 gram? Isn't it 50? No. You are going to add 2 grams of zinc into your calculation as well. 50.0 cm cube of the copper 2 sulfate, and you just assume to be 50.0 gram. Okay, together with 2.0 gram of zinc powder. So add it together. You may get it as 52.0. While this one, it is problem of this reaction mixture, 4.2 gram per 4.2 joule per gram per Kelvin. And the delta T, it is done by extrapolation. You project the maximum temperature rise. Do you realize? And then you do the MC30. So the MC30 refers to the reaction mixture. So also it also happened in the container. So it's 52.0 gram times 4.2 joule per gram per Kelvin times 11.9 Kelvin. Here comes 2.60 kilojoule. The number of moles of copper 2 sulfate reacted as said before, it is what? It is the limiting reactant. So you use this as a denominator and calculate. And you'll finally get the displacement reaction with this enthalpy change being minus 208 kilojoule per mole. Remember, it is an exothermic reaction. So I mark it as minus. Is that clear? Questions? Do you find the techniques of doing extrapolation difficult? A bit, right? So don't worry, you will have chance to do it in your class practice. So 34.7. Now this time, this type of thermal extrapolation would also happen in some other graph. This is thermometric titration. Was carried out by using 1.00 mole per dm cube sodium hydroxide solution and dilute hydroxide of unknown concentration. And then you are going to do it into a suitable apparatus, blah, 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 right? And 5 cm cube of portions of acid you added subsequently, and you're going to measure the mixture and calculate the to measure the temperature. And originally it is at 20.0 cm as at degrees Celsius. So this is our graph. Originally it is 20.0. Mark it here. So suggest a suitable apparatus for carrying out the above experiment. What container, what material container should be used? What do you think? That the design is more or less similar to what you have right, while you do the neutralization. You use what?
Polystyrene cup.
Yep, polystyrene cup. So in chemistry, we would use the term expanded polystyrene cup, or you use foam plastic cup, right? But in chemistry, we usually tell the chemical name, right? Expanded over polystyrene. Expanded polystyrene. Okay, is that clear? So, while the whole setup is more or less similar. with a lid, right? Of course, somebody will plan to use a stirrer for help, but in practical sense, we will not use. You can use stirrer, or you can swirl the polystyrene cup while you do experiment. It will also help solve that. What is the greatest temperature rise of a solution mixture estimated from the graph? Now this time you use what? We'll use extrapolation. Now, how? Can you locate the equivalence point? Equivalence point, which means that the two chemicals just react together without anything in excess.
28.2 or something like that.
32?
28.1 or 2.
20.1 or 2?
28.
28. Where, which point? 28.
佢畫兩條直線，跟住之後就
So how will you locate? So you draw that two lines, right? So this is our way to do, right? This another line. Yes, this is the one. Do you find it? So this is the imaginary maximum temperature rise. It is 20 what? 28.
28.4.
3 or 0.4, right? Because my line is already a little bit thick. It doesn't matter. 28.3 to 28.4 degrees Celsius. So this is our maximum. While the equivalence point, the exit just react is 33. It's 33.0, right? Isn't it? So you use these two data for help, right? 33.0 cm cube of exit just react. Do you realize? So it is just a like this. Do you realize? Okay. So what is the delta T? Delta T, I use this data for help. Delta T 28.3, for example, minus the initial temperature is 20.0, right? Do you find it? So what is the answer? It is 8.3 degrees Celsius. So it's not 33 now. It's 23. It is 32.5. Now, according to our of drawing, isn't it right? It's 32.5. It's just a quarter, right, of this grid line. It's just a quarter. Now, determine the concentration of a hydrochloric acid. So you are going to do the calculations that later on here. So you are going to find out NaOH AQ plus HCl to form NaCl AQ plus H2O with 1 molar, 50.0 cm cube. Wow, this is, I don't know what molar, but it is 32.5 cm cube. So according to this equation, the number of moles of HCl is equal to number of moles of NaOH, okay, which is 1.00 molar. 50.0 times minus 3 dm cube m times 3. Do you still remember? And it is 0.0500 mole. Okay, this is the run, and you are going to find out the concentration of HCl. Of course, we are going to find out in mole per dm cube, right? Which is calculated as 0.0500 mole over is volume, which is 32.5 times 10 to the power minus 3 dm cube. So the answer is 1.5 something. What is your calculation? What do you calculate? 1.5 something. 記得
1.54 mole per dm cube.
Yes, 1.54 mole per dm cube. So this is the answer, right? This is B part. So there is a slight discrepancy between yours and mine. It doesn't matter because the delta T is different. The volume of the HCl may be different. So a slight difference between them. But the focusing point is to check whether or not you can do the extrapolation with great care. And they will accept a certain range of the answer in DSE. Remember the chapter unit, mole per dm cube. D, calculate the enthalpy change of neutralization of HCl with NaOH. We've given the density of the solution mixture being this, specific capacity reaction mixture being this. They try to use it as water, right? Of course, it is just as a rough estimation. The point is, D, how you get that? How you get that D? You're going to find out the MC30, right? To get to the amount of heat released. So the MC30 refers all to the solution mixture. M, what is the M? Remember, you are going to make an addition of the two. One for acid, one for alkaline. The specific capacity. The delta T. As set, I calculated as 8.3, is it? So you're going to get the answer. What is that? 2860 joule, or 2.86 kilojoule. Okay, you use this data for help. Number of moles of water to be formed. It is equal to what? What I've just added initially. NaOH. NaOH, originally I make it as 0.0500 mole, isn't it? So it is the exactly what you have got it from here for the complete reaction. So the delta H of neutralization, is it in standard state? Is it in standard condition? No, not mentioned, right? Because, but I will know that it's not in standard condition. Why? You measure it as you measure the initial temperature of solution being 20.0 degrees Celsius. So it is not a standard. So never, you need to draw something like this, okay? It's not correct. It's not correct. Remember, somebody has also suggested that, okay, the acid is not in 1 molar concentration. So it is not in standard condition. Do you realize it's not in standard condition? So, but in your calculations, even though it's not 1.00 molar, it's also okay. Because it's just a, you may see there's just a division. It's used to save your chemical. Theoretically, you can do such calculations, but the most crucial point is to check whether or not the condition is standard. You have to check what? You have to check the temperature. The temperature, okay? Is somewhat with that. It's very crucial. So because I mark it as delta H, remember to put a negative sign. 2.6 x6 kilojoule over 0.0500 mole. So you get the answer is minus 57.2 kilojoule per mole. Is that clear? You get it? When compare this data with this data, how come this value is different from that of the HCl and NaOH?又嚟 again. Do you realize that, right? This is also commonly asked in your DSE. Any questions? Anything, any idea about that? What do you think? This is the last question. Yes, it's less negative. First of all, it's less negative. Tell me, yes, that's right. It is less negative. But you have to tell me why. What is the difference between the two? The difference lies on this, right? Please elaborate. The reaction of the two of the original questions involving the strong acid, strong alkali reaction, but this time it is just a strong acid, weak alkali. So weak alkali here it's ammonia. So what is the difference? Some energy is involved in the what?
Ionization of ammonia.
Yes, it is needed for is needed for ionization of alkali before neutralization. Even though you would have produced, you will talk about the production of 1 mole of water, right, to be formed. This delta T value, it is a delta H value, it is less negative than you compare with strong acid, strong alkali one. Do you find it? So this is what by undergoing ionization before neutralization, such that we can get hydroxide ions, okay, to make this reaction happen. Do you find it? So remember, this is what I would like to leave it, all of you, to have a try on that. Any questions so far? So this is nearly the end of this chapter. Now we come to our summary today. we come to the design involving the delta H of reaction between the two solutions and one solid and one solution. Now the design is more or less similar, but the data treatment will make a much difference because the speed, the rate of a reaction is much different. For the quick reaction, you simply measure the thermometer reading that you can get the maximum temperature. But for slow reaction, you use one graphical method. So what is that graphical method? We do it as extrapolation in order to find out the maximum temperature, and so as to do the subsequent calculations as follows. So this is one of the very important technique. Any questions so far? Which part do you find it easy or difficult? You find it easy or difficult or what? Now let me know your understanding of today's topic. So all of you, please do question 24, long crack 24 as your follow-up, okay, today. Okay. Now, if not, I'll see you guys in the next lesson. I will show you the supplementary lesson schedule shortly today. Please stay tuned. Bye-bye.